Welcome to Lecture 4. So continuing on with John Dalton's atomic theory here. Again, these aren't always true, but they are very helpful to know. This is kind of what an atom looks like for the most part. There's protons and neutrons, and this kind of dotted line is your nucleus. So that's the center. It has a very positive charge. Electrons are negative, and they will be zooming around in electron orbits. Electron orbits do not look like this. It is much more complicated than this, actually. The electrons will never have a perfect orbit. They're going to be bouncing around everywhere. It can be very complex, and I'm not going to super get into it because that's when you get into inorganic chemistry and quantitative analysis chemistry and organic chemistry, and you get higher up. Then you could take a step back and you could actually learn what this looks like. But for general chemistry, this is what we show you guys, and this is kind of the thing that you guys got to wrap your head around at first. So that way, once you understand this, you can start to understand a little bit more and be like, okay, so it's not actually like that. This is how it really is. So we have section 1.6, the discovery of the electron. So here is a cathode ray tube. So cathoids are kind of like negative tubes of sorts. So you got your cathode is negative here, and your anode, which is positive. So cathodes, you can remember, sorry for the cat lovers out there, cats are kind of crazy and they might be negative. So if you remember a mean negative cat, I love cats, trust me, I really do. But for this example specifically, it helps me remember it. So come up with a different metaphor or example if it helps you remember it more. But for me, I remember a mean negative cat, and that's how I know cathodes are the negative side and anodes are just the other one, which is positive. So if I know cathodes are negative and the only other thing is an anode, then it has to be positive because cathode is negative. So that's how I remember it. These are the cathode rays. So this is an actual real life version of it. And this is a partially evacuated glass tube, which basically means the air was taken out of this tube and the glass was melted on either end, and these voltage kind of like wires were put on, and the electrons are going here, and we can see the electrons because there is a gas inside. So kind of an example of this would be a CRT. I don't really know what a CRT is. I think I'm too young for this, but this is what it looks like. So if you ever saw this at like your grandparents' place, it does kind of the same thing. So a charge to mass ratio of the electron. This is another way you could do it. Electrons will deflect here when electrically charged plates are present. This is another evacuated tube. Remember, the air is taken out. This is a magnet right here. This weird looking thing is a magnet. It's hooked up to some electricity with our cathode and anode, and when the electrons are put forwards in, the beams are deflected. So the electrons actually travel in different ways. It's not straight on, it's just different ways. And because the magnet is changing the direction that the electrons goes. So the electric and magnetic fields deflect the electron beam, and they're going different ways. So the electrically charged plates as well as the magnetic field are causing the electrons to bend and travel in different paths. They're deflected beams. So electrons will deflect here when the electrically charged plates are present. So what does this say about electrons? It says that electrons themselves have a charge. So similar to the properties of magnets, as in like north and south poles, magnets have north and south poles, but basically opposites will attract, and then like ones like north and south will repel each other. That's why if you put two magnets together, they'll snap together, and if you flip them over, they'll repel each other, and there's like this invisible force that can't force the magnets together. That's that magnetic field, that's that magnetic charge that doesn't want to be near the positive side, or doesn't want to be near the negative side. And that's kind of even helps with the gravitational spin of the Earth, as in we have a North Pole and a South Pole, and we're kind of rotating on our axis, and there's even Earth's magnetic field, which is a whole other topic. But for here, getting really small, we have the properties of the electrical charge. Here, just for example, this isn't how it actually looks, is we have a positive red and a negative yellow, and opposites will attract each other, and like charges will repel. So the nucleus is positive. It's full of protons and neutrons. So protons are positively charged, pro, meaning like positive, and electrons are negatively charged. So that's why those electrons are orbiting around that really, really positive nucleus, right? When they're together like this, they will cancel out. This is why atoms are relatively stable, is because that positive charge of the nucleus will cancel out with the amount of electrons going around it for the most part. So here, this is a experiment that was done, and there was an atomizer, which basically turns this into really, really fine mist. There was a positively charged plate and a negatively charged plate, and the atoms were put in between. So charged oil droplets were suspended in an electric field with a light source and an ionizing radiation. Again, there was a lot of radiation used back then. So this is basically how they did it. They measured the charge of them in coulombs. So the important find in this work is that an electron has a charge of 1.6 times 10 to the negative 19 coulombs, which is a type of energy. Since the mass-charge ratio was already known, the mass of an electron was calculated to be 9.17 times 10 to the negative 31 kilograms. That is 30 zeros that way. 0.30 zeros. 917 kilograms. Very, very, very small. And if you put this in grams, you'd even add 3 more zeros, so it'd be negative 4, I think? I'm not sure. So section 1.7 is the structure of an atom, so now we know. This is the first model that was kind of done. This is the scientists back then were kind of unsure, because science has progressed extremely heavily over the past even 500 years or so. Even the past 100 years, science has progressed a lot. But they used to think this is what an atom looks like. It's a sphere of positive charge where all those protons and neutrons are. They didn't really know about protons and neutrons too much, but they called it the plum pudding model. So you got your pudding, and there's a bunch of plums in it, and so this is why they called it the plum pudding model, because there's electrons just spaced out in the sphere of positive charge. This is the one that we know about today. This is the actual atom. This is a lot more like what it looks like. How did we really find about this? So this experiment really helped. It's really important for you guys to know this. I'd recommend doing your own research as well. So this is Rutherford's gold foil experiment. So he had this entire detector around here, and he had a piece of gold foil, and he had a source of kind of like light with the lead, and he put alpha particles through it. So an alpha particle is the nucleus from a helium atom. So a helium atom has a proton, 2 protons, and 2 neutrons, I think. And a few alpha particles were deflected through large angles. So some went through fine, little or no deflection, but some went really wide, and some were even deflected back. What happened was most alpha particles were not deflected, and they passed through. These are the atoms of the gold foil. They passed through. Some hit the nucleus of gold. So some of these helium atoms bounced off of the nucleus and were repelled, because the nucleus from a helium atom is positive. Nucleuses are positively charged. Well, so is these gold atoms. Their nucleus is positively charged. So when positive meets positive really close, it is reflected back. So this gold foil is not going anywhere, but these helium atoms are in a gaseous state, so they will just bounce off or get really close and then get deflected like a magnet if they got too close. So that's why some of them bounced off. The predicted result was that everything would just pass through. The actual result is that the gold atom nuclei were bouncing or repelling the helium nuclei. This is how they discovered, okay, there must be some dense forms in there of what they discovered to be protons and neutrons in order for this to actually happen. So the major conclusions from this was that a small, relatively heavy, positively charged body, the nucleus, must be at the center of each atom. This is why a small fraction of the alpha particles are significantly deflected by the gold foil. They were deflected by those gold atoms. And this is why a small fraction of the alpha particles, or those helium nuclei, are slightly deflected by the gold foil. So now this is kind of what they got an idea of, and this is a lot more accurate about what is actually happening. You got these shells of electrons around this positively charged nuclei. Don't worry too much about the electron shells. We will talk about those later. So the major conclusions is that the volume occupied by an atom must consist of a large amount of empty space. So the empty space between the nuclei and the electrons. This is why most of the alpha particles passed directly through the gold foil. They weren't really repelled by the electrons bouncing around everywhere. They were still able to get through. There are negatively charged electrons that reside outside the nucleus. And so those are the ones that are flying around randomly. So section 1.8, subatomic particles, protons, neutrons, and electrons. So that's what subatomic particles are, so even smaller. This is important. You guys are going to want to kind of memorize this table. This is going to be helpful for conversions later. I myself don't really ever work with charges, but it really depends on what the type of science you're going into. It might behoove you, or it might be good for you to memorize the charges as well as their mass and this. Mass is an AMU, or atomic units, basically. It's just a fancy term for just a different type of mass for a proton, neutron, and electron. Instead of having to write mass in kilograms here, you can just write mass AMU. So the mass of a proton, neutron are basically 1, and electrons are basically very close to 0. So that's why when you're doing problems that rely on mass, you're not really going to be looking at how much the electron weighs. If you're looking for how much an atom weighs, you're going to be looking at the protons and the neutrons. The protons and neutrons will give an atom its weight, and in turn, it will give it special properties. If you look on the periodic table in the bottom right, those are going to be the really, really big 100-something AMU kind of masses. And if you look at hydrogen, basically 1.008, oxygen is 15.999, or you normally use 16, and carbon is 12.011 or 12.01. And so when you're doing problems that say, oh, how many atoms are in 5 moles of CO2? So you take CO2, you take your carbon, 12.01, and your 2 oxygens, 16 each. That's 16 plus 16 plus 12 is 32 plus... Okay, so 44 about. You have 44 AMU in 1 CO2, 1 mole of CO2. And so if you have 5 moles of CO2, you just multiply 5 times 44, and then you will get how many atoms are in it. And then of course you also multiply by Avogadro's constant, the 6.032 times 10 to the 28, something about that. But that'll tell you the amount of like particles or atoms in something. So I recommend going back, and now that you kind of know this, working with AMU or working with actually the mass in kilograms. Remember, if it's in kilograms and you're trying to find grams, you have to put 1,000 grams in 1 kilogram, or 0.001 kilograms in a gram. You have to convert grams to kilograms. Remember to cancel out the units in a fraction. Otherwise, you're not going to get it right. So remember, make sure your units are canceling out so you're only left with what you want. I highly recommend going off and looking up some more diagrams of atoms, diagrams of the nucleus, so that way you guys can get a little more practice with it, and a little more practice in converting the masses, and even going through the periodic table and finding out, okay, why does this equal this? How many protons are in this element? How many neutrons are in this element? And keep in mind that electrons really don't matter until later. So just for the mass of an atom, only look at the protons and neutrons, and we will cover electrons later. All right, I will see you guys in lecture 5.